Imagine standing at the ultimate edge of perception, looking out into a realm where light itself has not yet had enough time to reach human instruments. Beyond the most distant galaxies, and beyond the ancient glow of the cosmic microwave background, lies a mystery that continues to challenge theoretical physics. What actually exists beyond the limit of our sight? Is it simply an endless continuation of stars and galaxies, a boundless empty void? Or perhaps something entirely alien to our current understanding of physical law? To address these questions, we must first recognize a fundamental constraint of observational science. Because light travels at a constant finite speed, and our universe possesses a finite age of roughly 13.8 billion years, our view of space is strictly bounded. Beyond this cosmic horizon sits a vast region that remains fundamentally unseen, forcing scientists to rely on mathematical models, theoretical physics, and careful inferences rather than direct observational data. Today, we will explore what's on the other side of the universe. We will examine the leading hypotheses proposed by cosmologists, taking care to distinguish between established physical facts and speculative theoretical models. If you enjoy exploring the deep questions of our cosmos, please consider liking this video and subscribing for more scientific journeys. Before we begin, leave a comment below sharing where you are watching from today and what time it is wherever you are on Earth. To understand where our vision ends, we must first confront one of the most fundamental laws of modern physics, the speed of light. Light does not travel instantaneously across space. It propagates through a vacuum at a fixed velocity of approximately 186,000 miles per second, or nearly 300,000 kilometers per second. Because this speed is constant, every photon arriving at our telescopes is a historical artifact. Looking out into the depths of space is inherently equivalent to looking backward through time. When we observe the Moon, we see it as it existed 1.3 seconds ago. When we view the Sun, we behold light that left its surface over 8 minutes prior. Nearby stars appear as they existed years or decades ago, while distant galaxies reveal their structures as they were millions or even billions of years in the past. This cosmic delay creates an inescapable perceptual boundary. Because the universe has a finite age, estimated by modern cosmological measurements to be roughly 13.8 billion years, light has only had a limited amount of time to travel across space since the primordial origin of the cosmos. This temporal limitation establishes what astrophysicists refer to as the particle horizon. The particle horizon defines the maximum distance from which particles of light or gravitational radiation could have reached an observer on Earth since the beginning of cosmic time. If space were completely static and motionless, the maximum observable distance in any direction would simply equal 13.8 billion light-years. However, observational data gathered over the past century have conclusively demonstrated that space is not static. Instead, the cosmos has been continuously expanding since the Big Bang. This metric expansion of space fundamentally alters spatial geometry and dramatically extends the actual physical distance to the edge of what we can observe. As ancient light travels toward Earth across billions of years, the intervening space through which it moves expands. The photon traverses a stretch of space that is continuously lengthening, much like an athlete running on an ever-extending treadmill. By the time that ancient photon completes its journey and strikes an observatory detector on Earth, the original source galaxy has been carried far deeper into space by cosmic expansion. When astrophysicists account for this expansion history using general relativity, they calculate that the current physical distance to the most distant observable light source is not 13.8 billion light-years, but approximately 46.5 billion light-years. Consequently, the total sphere of space accessible to human instruments, known as the observable universe, spans a diameter of roughly 93 billion light-years. Yet even within this colossal sphere of 93 billion light-years, our electromagnetic sight encounters an impenetrable physical barrier long before reaching the theoretical particle horizon itself. This limit is known as the cosmic microwave background radiation. In the earliest moments following the Big Bang, the universe was far too hot, dense, and energetic for stable atoms to form. Space was filled with an opaque, glowing plasma composed of free protons, electrons, and high-energy photons. Light could not travel freely through this dense environment. Photons were continuously bouncing off free electrons in a state of constant scattering. For the first 380,000 years of cosmic history, the entire universe remained completely opaque. This opaque condition persisted until a critical transition, known as the epoch of recombination. As space expanded, its energy density dropped and its temperature cooled to approximately 3000 Kelvin. At this thermodynamic threshold, atomic nuclei were finally able to capture free electrons, forming the first neutral hydrogen and helium atoms. With the free electrons suddenly bound inside atoms, space instantly became transparent. The trapped photons were liberated all at once, streaming freely across the expanding cosmos in every direction. Today, after 13.8 billion years of spatial expansion, those ancient photons have been stretched into longer, cooler microwave wavelengths, arriving at Earth as a pervasive, uniform sea of radiation at a temperature of approximately 2.7 Kelvin above absolute zero. The cosmic microwave background radiation represents the absolute boundary of direct electromagnetic observation. We cannot take an optical photograph or collect an infrared image of anything that occurred prior to the epoch of recombination, because no free-streaming light existed before that moment. When we point our most advanced space telescopes toward the deepest reaches of the cosmos, the cosmic microwave background appears as the ultimate background surface in every direction. It acts as a glowing shell surrounding our observational domain, providing an image of the young cosmos as it appeared just 380,000 years after its formation. It is vital to emphasize a fundamental scientific distinction regarding this boundary. The horizon of the observable universe is not a physical wall in space, nor does it imply that the universe ends at this boundary. Rather, it is an observational limit defined entirely by the speed of light and the age of the cosmos. An observer located in a distant galaxy 40 billion light-years away from Earth would possess their own unique observable universe sphere centered on their location. Their horizon would overlap with ours, while simultaneously encompassing vast regions of space that are completely hidden from human sight. What lies beyond our specific observable bubble remains impossible to observe directly, forcing cosmologists to rely on mathematical modeling, theoretical physics, and careful scientific inference to reconstruct what might exist on the other side. When cosmologists attempt to extrapolate what lies beyond the 46.5 billion light-year boundary of our observable universe, the most natural starting point relies on one of the foundational tenets of modern astrophysics, the cosmological principle. This principle posits a remarkably elegant concept about the large-scale architecture of space. It states that, when viewed on sufficiently massive scales, the universe is both homogeneous and isotropic. Homogeneity means that the distribution of matter and energy is uniform throughout space, showing no preferred central location or peculiar privileged regions. Isotropy means that space looks identical in every direction, displaying no preferred orientation or unique structural alignment. The cosmological principle is not merely an abstract philosophical assumption, it is supported by extensive empirical evidence gathered within our observable domain. Large-scale astronomical surveys have repeatedly confirmed that once we zoom out beyond individual galaxy clusters to scales larger than several hundred million light-years, the universe resembles a remarkably uniform cosmic web. The distribution of matter, the frequency of cosmic structures, and the temperature fluctuations recorded in the cosmic microwave background all demonstrate exceptional consistency in every direction we look. If we apply the cosmological principle to the unobserved space beyond our horizon, the simplest and most conservative scientific deduction is often called the hypothesis of endless spatial continuation, or the more of the same model. Under this theoretical framework, crossing the physical boundary of our particle horizon would not reveal any sudden edge, dramatic wall, or sudden transition in physical law. Instead, an observer travelling past our observational limit would simply encounter more of what we see locally: vast filaments of dark matter, cosmic voids, superclusters of galaxies, millions of stars, planetary systems, and interstellar dust. Under this model, the unobserved space functions as a seamless, uninterrupted extension of the local cosmos. A traveller standing at the current edge of our observable sphere would look out and see another observable sphere of their own, filled with galaxies that are completely invisible from our perspective on Earth. To that distant observer, our galaxy would sit near the edge of their observational horizon, while their position would mark the centre of their own distinct observational cosmic bubble. This brings us to a crucial question in theoretical physics. If space continues seamlessly beyond our horizon, does it extend indefinitely, or is it vast yet fundamentally finite? The answer depends heavily on the global curvature and topological properties of the universe. If the universe possesses a flat geometry on global scales and lacks any closed global topology, general relativity dictates that space must be infinite in physical extent. An infinite universe operating under the cosmological principle leads to extraordinary theoretical consequences that push the boundaries of physics and probability theory. In an infinite space filled with a finite density of matter, the number of possible particle configurations within any given volume, such as an observable universe bubble, is astronomically large, but ultimately finite. Quantum mechanics dictates that within a region the size of our observable universe, there are only a finite number of ways that subatomic particles can be arranged. If space is truly infinite in volume, simple probability theory implies that every single possible configuration of matter must repeat an infinite number of times across the vast expanse. Under these extreme theoretical assumptions, far beyond our observable horizon, there would exist unobservable regions of space that mirror our local universe with incredible precision. There would be regions where galaxies formed in nearly identical patterns, stars evolved along parallel paths, and planetary systems organized into familiar solar architectures. Somewhere across an infinite volume of space, there would theoretically exist exact duplicates of our solar system, our planet, and even our historical timeline. Theoretical physicists have calculated that such identical regions, if they exist, would be located at mind-boggling distances, roughly 10 to the power of 10 to the power of 115 meters away. However, scientific rigor requires maintaining a strict distinction between mathematically consistent theoretical models and established empirical truths. While the cosmological principle provides a reliable framework for understanding our local cosmic neighborhood, extrapolating it infinitely across unobservable space remains a theoretical hypothesis. We cannot assume with absolute certainty that homogeneity and isotropy hold true infinitely across regions that can never transmit signals to us. It is entirely plausible that the cosmological principle only applies locally or regionally. Beyond our observable horizon, the large-scale distribution of matter could gradually shift. Density fluctuations could increase, average temperatures could vary, or the fundamental ratio of dark matter to baryonic matter could slowly change across gargantuan spatial gradients. The hypothesis of endless continuation offers a highly compelling, mathematically elegant starting point that requires no new physics, yet it remains an unproven extrapolation of the patterns we observe from our isolated vantage point in the cosmos. Beyond the simple idea of infinite flat space lies the fascinating realm of cosmic topology. To understand what might exist on the other side of our observational horizon, astrophysicists must carefully distinguish between the geometry of the universe and its overall shape or topology. Geometry describes the local curvature of space, which can be flat, positively curved like a sphere, or negatively curved like a saddle. Topology, on the other hand, describes the global connectivity of space, how different regions of space are bound together on the largest imaginable scales. Measurements collected by advanced space missions, including NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite, have analysed the tiny temperature fluctuations in the cosmic microwave background with extraordinary precision. These empirical observations demonstrate that, on local and regional scales, our universe appears remarkably flat, with a margin of error of less than 1%. In a geometrically flat space, parallel lines of light remain parallel forever, and the interior angles of a cosmic triangle sum precisely to 180 degrees. However, a fundamental insight of mathematical topology is that a space can be locally flat while simultaneously possessing a closed, finite global topology. The most classic analogy used by physicists to illustrate this concept is a two-dimensional video game environment, such as the classic game Pac-Man. In these games, when a character travels off the right edge of the screen, they instantly reappear on the left edge. If they travel off the top boundary, they emerge from the bottom. The screen itself possesses flat geometry at every local point, yet its overall global topology forms a closed, continuous loop without any physical boundaries or edges. When translated into three spatial dimensions, this multiply connected geometry is known as a three-torus, or colloquially, a donut-shaped universe. In a three-torus universe, space is finite in total volume, yet it contains no physical wall, border, or edge anywhere within its structure. If an observer were to travel in a straight line through a three-torus cosmos, they would never hit a barrier or encounter an empty void on the other side. Instead, after traveling a fixed colossal distance, they would eventually return to their exact starting point from the opposite direction. If our universe possesses a three-torus topology, the implications for what lies on the other side of our observable horizon are profound. What we perceive as the unobserved space beyond our particle horizon would not be an endless ocean of brand new galaxies. Instead, the other side of the universe would simply be a continuation of the exact same space we inhabit, looping around on itself through extraspatial connectivity. In such a model, light emitted by distant galaxies billions of years ago would wrap around the curvature of the torus multiple times. Under specific topological conditions, an observer looking out toward the edge of the visible horizon might actually be seeing the ancient past of our own local cosmic neighborhood. Light leaving our Milky Way galaxy in the distant past could travel along a closed topological loop, eventually arriving back at Earth billions of years later from the opposite side of space. Theoretically, astronomical instruments could detect ghost images of our own galaxy as it appeared in its early evolutionary stages, viewed from multiple directions across the sky. Physicists have spent decades searching for observational evidence that could prove or disprove a compact, closed topology like the three-torus. One of the primary observational methods involves searching for matching patterns in the cosmic microwave background, a technique known as searching for circles in the sky. If the observable universe sphere is larger than the fundamental repeating size of a closed topological torus, the sphere of the cosmic microwave background would intersect with itself. This intersection would produce pairs of identical temperature fluctuation patterns, forming matching circles on opposite sides of the microwave sky. Astrophysicists have conducted exhaustive statistical algorithms analyzing Planck satellite data to detect these matching cosmic circles. Thus far, high-precision searches have yielded no definitive, undisputed evidence of repeating matching circles or ghost images of distant structures. The lack of observational detection allows scientists to establish strict lower bounds on the potential scale of cosmic topology. If the universe is indeed a closed three-torus or another compact topological manifold, its fundamental repeat length must be larger than the diameter of our observable sphere, meaning any repeating loop must extend far beyond 93 billion light-years. Therefore, while topological models like the three-torus remain completely valid within the mathematical framework of general relativity, they remain purely theoretical possibilities at present. We must carefully hedge our conclusions. Geometry shows us that space is exceptionally flat, but topology leaves open the possibility that the other side of the universe is simply this side of the universe, wrapped around a vast invisible loop that exceeds our current capacity to observe. To explore one of the most prominent theoretical possibilities for what lies beyond our cosmic horizon, we must turn to the physics of the early universe, specifically the model known as cosmic inflation. Developed in the early 1980s by physicists Alan Guth, Andre Linde, and Paul Steinhardt, cosmic inflation was originally proposed to solve several major puzzles in standard Big Bang cosmology, such as why the observed universe appears so flat, smooth, and uniform across vast scales. According to standard inflationary theory, an extremely brief fraction of a second after the initial singularity, roughly between 10 to the power of minus 36 seconds and 10 to the power of minus 32 seconds, the universe experienced an extraordinary exponential expansion. Driven by a high-energy quantum field known as the inflaton field, space expanded at a rate far exceeding the speed of light. During this fleeting epoch, a subatomic patch of space stretched by a factor of at least 10 to the power of 26, smoothing out any curvature and diluting pre-existing irregularities into near-perfect homogeneity. When this exponential growth halted, the massive potential energy stored within the inflaton field decayed into a hot, dense sea of subatomic particles, initiating the standard Big Bang expansion phase that continues to this day. However, detailed theoretical analyses of inflation revealed an unexpected consequence. In many mathematical variations of the inflaton field, quantum mechanics introduces a dramatic twist. Inflation does not end everywhere simultaneously. Because the inflaton field is subject to quantum fluctuations, different regions of expanding space decay at different times. While inflation ends in specific localized regions, decaying into hot matter and radiation, the surrounding space continues to expand exponentially at a relentless pace. This theoretical framework is known as eternal inflation, a paradigm originally pioneered by cosmologist Andre Linde. In eternal inflation, quantum fluctuations cause the inflaton field to drop to its ground state in scattered, isolated pockets. In these specific pockets, the exponential expansion ceases, and a conventional, hot, expanding cosmos is born. These decoupled regions are widely referred to as bubble universes or pocket universes. While a pocket universe experiences a transition to standard Big Bang expansion, the vast space surrounding it continues to inflate exponentially. Because the rate of exponential inflation is exponentially faster than the expansion rate within a mature pocket universe, the inflating space between bubbles grows far more rapidly than the individual bubbles themselves. As a result, new pocket universes are continuously generated across an ever-expanding, eternal background space. If eternal inflation accurately describes reality, the implications for what lies on the other side of our observable universe are staggering. Under this framework, our vast 93 billion light-year observable bubble, and indeed the entire unobserved space produced by our local Big Bang, is merely one single pocket universe among an infinite expanding sea of other bubble universes. This grand cosmic structure is commonly termed the inflationary multiverse, or Level 2 multiverse in the classification scheme formulated by cosmologist Max Tegmark. Crossing the distant boundary of our pocket universe would not lead to an ordinary continuation of stars and galaxies, nor would it lead to a simple topological loop. Instead, far beyond the outer reaches of our local expansion zone, one would encounter the hyper-expanding false vacuum space of the inflating background space, a region where space itself is doubling in volume every fraction of a second. Beyond that chaotic, rapidly stretching intermediate region would sit completely separate bubble universes, each born from its own distinct decay event in the inflaton field. Furthermore, many theoretical physicists propose that adjacent pocket universes might possess entirely different physical characteristics. The precise values of fundamental physical constants, such as the strength of the gravitational force, the fine structure constant governing electromagnetism, the mass of subatomic particles, or the cosmological constant driving dark energy, may not be fixed, universal constants across all reality. Instead, these values could be selected dynamically during the symmetry-breaking phase transitions that occur when inflation ends within a specific pocket universe. In string theory, this concept merges with the idea of the string landscape, which posits that there are as many as 10 to the power of 500 mathematically consistent ways to compactify extraspatial dimensions, each yielding a unique set of low-energy physical laws. If eternal inflation samples this vast string landscape, different bubble universes on the other side of ours could operate under completely alien physical frameworks. In some neighboring pocket universes, gravity might be so overwhelmingly strong that the entire bubble collapses back into a singularity within a few seconds of its formation. In others, the electromagnetic force might be too weak to bind electrons to atomic nuclei, rendering chemistry and complex matter impossible. Still others might be dominated by a vast cosmological constant, causing space to expand so violently that subatomic particles are pulled apart before stars or galaxies can ever condense. According to this framework, Our local universe appears uniquely fine-tuned for life, simply because intelligent observers can only emerge within rare pocket universes whose local physical laws permit the stability of complex structures. It is crucial, however, to maintain a strict scientific distinction between what has been experimentally verified and what remains theoretical extrapolation. Eternal inflation is an extremely compelling mathematical consequence of merging general relativity, classical field theory, and quantum mechanics, but it remains an unproven theoretical hypothesis. Direct observational testing of other bubble universes is inherently restricted by the fundamental laws of relativity. Because the space intervening between pocket universes expands at superluminal speeds, light signals emitted by a neighbouring bubble universe can never traverse the intervening distance to reach our instruments. Some theoretical models suggest that if two adjacent pocket universes collided early in their evolutionary histories, the event might leave a subtle circular imprint or temperature anomaly in the cosmic microwave background. Astrophysicists have searched extensively through data collected by orbital observatories like the Planck satellite for these theoretical cosmic bruises. While a few thermal anomalies have been identified, none have yielded conclusive, statistically undeniable evidence of a past bubble collision. Therefore, when discussing the possibility of an eternal inflation background filled with floating bubble universes, we are operating at the cutting edge of theoretical physics. The bubble universe hypothesis offers an extraordinarily rich answer to what might lie beyond our horizon, yet it resides at the boundary where empirical astronomy meets advanced theoretical physics, waiting for future breakthroughs to provide a definitive test. While many theoretical hypotheses about what lies beyond our cosmic horizon rely on mathematical models extrapolated from local physics, astronomers have also investigated subtle observational anomalies within our observable sphere that might offer indirect clues. One of the most intriguing and controversial of these phenomena is the concept known as dark flow. First identified in the late 2000s by a team of astrophysicists led by Alexander Kashlinsky at NASA's Goddard Space Flight Center, dark flow refers to an unexpected, coherent movement of distant galaxy clusters drifting in a uniform direction across cosmic space. According to the standard cosmological model, known as the lambda cold dark matter model, the expansion of the universe on large scales should be isotropic and random. Individual galaxy clusters possess localized, peculiar velocities, movements caused by the gravitational tug of nearby structures, such as neighboring clusters or superclusters. However, when cosmologists average these peculiar velocities over immense volumes of space containing thousands of galaxy clusters, the peculiar velocities should cancel out. On the largest scales, matter across the universe ought to be expanding uniformly in all directions, anchored to the rest frame of the cosmic microwave background. In 2008, Kashlinsky and his collaborators published findings that appeared to challenge this standard assumption. By analyzing the kinematic Sunyaev-Zeldovich effect, a phenomenon where high-energy electrons within galaxy clusters scatter photons from the cosmic microwave background, subtly altering their energy, the team measured the peculiar velocities of hundreds of massive galaxy clusters. Their initial statistical analysis revealed that a vast collection of galaxy clusters, spanning distances out to billions of light-years, appeared to be drifting together at a surprising velocity of approximately 600 to 1,000 kilometers per second. Even more unexpectedly, this massive stream of matter was moving in a specific, coherent direction toward a patch of sky located between the constellations of Centaurus and Vela. Subsequent studies by the same research group expanded the sample size to over 1,000 galaxy clusters and extended the observational range to nearly 2.5 billion light-years from Earth. According to their results, the overall systematic motion persisted across these vast distances without showing signs of decaying or slowing down. This suggested that an entire patch of our observable universe might be sliding as a single unified river through space. If dark flow represents a real physical motion rather than a statistical artifact or measurement error, it demands an explanation that extends beyond the boundaries of our observable sphere. A localized structure within our observable horizon, such as a massive supercluster, would not possess enough cumulative gravitational mass to pull such an immense volume of matter in a single uniform direction, without leaving obvious, visible footprints in optical and X-ray surveys. Therefore, the leading hypothesis proposed to explain dark flow points directly to what might exist on the other side of our cosmic horizon. Physicists hypothesize that during the epoch of cosmic inflation, primordial density fluctuations might have grown to colossal scales, far exceeding the size of our current particle horizon. As inflation ended, a massive concentration of matter and energy, a megastructure of unimaginable scale, might have formed just beyond the boundary of our observable universe. Although this hypothetical massive structure would remain completely invisible to our telescopes because its light has not had enough time to reach us, its gravitational influence would not be bound by the speed of light in the same way. The gravitational field established by this external mass distribution during the early universe could still exert a continuous, large-scale gravitational pull on the matter inside our observable bubble. In essence, dark flow would be the visible tug of an invisible giant, a gravitational shadow cast into our observable universe by colossal structures inhabiting the unobserved space beyond. However, scientific rigor demands a careful, critical examination of the evidence, and the dark flow hypothesis remains heavily debated within the scientific community. Measuring the kinematic Sunyaev-Zeldovich effect requires isolating extremely subtle temperature variations in the cosmic microwave background, measured in microkelvins, while filtering out overwhelming foreground noise from galactic dust, radio emissions, and atmospheric interference. Many independent teams of astrophysicists have attempted to replicate the dark flow measurements using different datasets and analytical techniques, yielding conflicting results. When the European Space Agency's Planck satellite released its ultra-high precision maps of the cosmic microwave background, multiple independent research teams analyzed the data to test the validity of the dark flow phenomenon. A prominent 2013 analysis conducted by the Planck collaboration found no statistically significant evidence supporting the systematic large-scale streaming motion reported by earlier studies. Their findings indicated that the velocity of galaxy clusters across large scales was completely consistent with standard isotropic expansion, with peculiar velocities falling well within the expected random fluctuations predicted by the standard cosmological model. Despite these findings, the dark flow debate is not entirely closed. Proponents of the hypothesis argue that differences in data filtering, cluster selection, and statistical weighting could explain why different observational techniques produce contrasting results. Some researchers suggest that while a global flow of thousands of kilometers per second across the entire visible universe is unlikely, localized regional flows caused by complex gravitational landscapes beyond the horizon cannot be entirely ruled out. The case of dark flow highlights the delicate nature of observational cosmology at the limits of our technology. It demonstrates how astrophysicists actively search for subtle anomalies that could act as a bridge between the observed universe and the unseen realm beyond. If dark flow is eventually confirmed by next-generation astronomical surveys, it would offer concrete observational evidence that massive, structured matter extends far beyond our particle horizon, actively shaping the dynamics of our local cosmic environment through long-range gravitational pull. If it is definitively disproven, it reinforces the power of the standard cosmological model, reminding us that the vast expanse beyond our sight may simply be a quiet, uniform continuation of the physics we observe today. When we ponder what exists on the other side of the universe, our minds naturally visualize traveling along a straight line across immense distances of three-dimensional space, passing trillions of stars and galaxies until we cross an outer frontier. However, theoretical physics suggests that our fundamental perception of space itself may be incomplete. What if the other side is not a destination located vast light-years away across length, width, and height, but rather a direction that lies perpendicular to our entire three-dimensional reality? To explore this mind-bending possibility, we must venture into the domain of high-energy physics, string theory, and Brane cosmology, where space is conceptualized as a multidimensional realm far richer than our senses perceive. In our daily lives, we navigate a physical reality defined by three spatial dimensions: up and down, left and right, forward and backward, along with a single dimension of time. For centuries, Classical physics operated under the assumption that these three spatial axes constituted the totality of physical space. Yet, when theoretical physicists attempt to unify Albert Einstein's theory of general relativity, which describes gravity on cosmic scales, with quantum mechanics, which governs the subatomic world, standard three-dimensional frameworks encounter severe mathematical breakdowns. To resolve these fundamental incompatibilities, theoretical frameworks such as superstring theory and its grander synthesis M-theory propose that the fundamental building blocks of the universe are not zero-dimensional point particles, but infinitely thin, vibrating one-dimensional strands of energy known as strings. For the mathematical equations of string theory to operate without inconsistencies or anomalous probabilities, space cannot consist of merely three spatial dimensions. Instead, these mathematical models require the existence of additional spatial dimensions, 10 dimensions in superstring theory and 11 dimensions in M-theory. To understand where these hidden higher dimensions might reside and what they imply for the nature of the cosmos, theoretical physicists generally propose two distinct paradigms. The first paradigm suggests that the extra dimensions are tightly curled up or compactified into infinitesimal geometric shapes known as Calabi-Yau manifolds at scales so minuscule that human instruments cannot resolve them. The second paradigm, however, offers a far more radical perspective known as large extra dimensions and Brane cosmology. In Brane cosmology, the word Brane is derived from membrane. Under this theoretical model, our entire observable universe, comprising all the stars, galaxies, planets, light and matter we can interact with, is hypothesized to be a three-dimensional surface, or a three-brane, floating inside a vast, higher-dimensional spatial landscape known as the bulk. Just as a two-dimensional piece of paper exists within a three-dimensional room, our three-dimensional universe may exist within an 11-dimensional hyperspace. If Brane cosmology reflects the true architecture of space, it completely redefines what might exist on the other side of our universe. Under this framework, crossing the boundary of the cosmos does not require traveling billions of light-years across our three-dimensional sheet of space. Instead, the other side could be located a fraction of a millimeter away, separated from us along a higher spatial dimension that human perception cannot directly access. We would be completely bounded to our three-dimensional brane, unable to peer or step off into the bulk, much like two-dimensional shadows cast upon a wall cannot step outward into the three-dimensional room. Furthermore, brane world models suggest that our universe might not be the only membrane floating within the bulk. The higher dimensional bulk could contain an array of parallel three-branes, each representing an independent, self-contained three-dimensional universe floating alongside ours. These parallel branes could drift through higher dimensional space completely parallel to our own, separated by invisible higher dimensional gaps. This model offers an elegant theoretical solution to one of the most perplexing mysteries in fundamental physics, the hierarchy problem. The hierarchy problem asks why the force of gravity is extraordinarily weak compared to the other fundamental forces of nature. For instance, a simple handheld toy magnet can easily overcome the gravitational pull of the entire Earth to pick up a small iron paperclip. Electromagnetism, the strong nuclear force, and the weak nuclear force are all vastly stronger than gravity by factors of trillions upon trillions. Brane cosmology explains this dramatic discrepancy by proposing a fundamental difference in how physics interacts with higher dimensions. In string theory, subatomic particles like photons, electrons, and quarks are represented by open strings, whose endpoints are firmly anchored to our three-dimensional brane. Because electromagnetic waves and matter particles are locked to our brane, they cannot detach or travel into the higher dimensional bulk. Light cannot escape our three-dimensional sheet, which explains why we cannot look across the higher dimension to see another parallel brane directly. In contrast, the carrier particle of gravity, the hypothetical graviton, is represented by a closed string that forms a seamless loop without endpoints. Because gravitons lack endpoints, they are not anchored to our three-dimensional brane. Gravitons are free to detach and propagate outward into the higher dimensional bulk. According to this hypothesis, gravity appears astonishingly weak in our daily experience because its field strength leaks out into the extra dimensions of the bulk, diluting its strength across higher dimensional space, while the other fundamental forces remain concentrated entirely on our localized three-dimensional brane. Taking this hypothesis further, cosmologists like Paul Steinhardt and Neil Turok developed the ekpyrotic model of the universe. In this cyclic cosmological framework, the Big Bang was not the original creation event of space and time from nothing, but rather the energetic result of a colossal collision between two parallel three-branes drifting through the higher dimensional bulk. Under the ekpyrotic model, two branes periodically attract one another across the extra dimension, colliding in a violent cataclysm that converts kinetic energy into a fresh sea of hot radiation and matter, simulating a Big Bang within each brane. After the collision, the branes bounce apart, expand, cool, and eventually draw back together over trillions of years to repeat the cycle indefinitely. Despite the mathematical beauty and conceptual power of brane cosmology and higher dimensional M-theory, scientific integrity requires acknowledging that these concepts remain entirely theoretical. At present, there is no direct empirical evidence confirming the existence of extraspatial dimensions, D-branes, or the higher dimensional bulk. High-energy particle colliders, such as the Large Hadron Collider at CERN, have conducted sophisticated experiments searching for signature evidence of gravitons escaping into extra dimensions, such as missing energy signatures during high-energy proton collisions. Thus far, all experimental data remains completely consistent with standard three-dimensional spatial physics. Brane cosmology provides a profound mathematical perspective on what might lie beyond our observational limit. It asks us to consider that the true boundary of our reality may not be a physical horizon in the distance, but the structural limits of our three-dimensional sheet itself, floating within a vast, unseen, higher-dimensional expanse. Among the most radical yet mathematically grounded hypotheses exploring what might exist beyond our observable horizon is the concept of a mirror anti-universe, extending backward from the Big Bang itself. Proposed by theoretical physicists including Latham Boyle, Kieran Finn, and Neil Turok, this framework offers a provocative solution to several long-standing puzzles in fundamental physics by re-evaluating the foundational symmetries that govern our universe. To understand this hypothesis, we must first examine one of the most bedrock principles in modern quantum field theory, CPT-symmetry. CPT-symmetry states that the physical laws governing a system must remain completely invariant under the simultaneous inversion of three fundamental properties: charge, parity, and time. Charge conjugation replaces every subatomic particle with its corresponding antiparticle, effectively swapping positive and negative charges. Parity inversion flips spatial coordinates, replacing a physical system with its precise left-right mirror image. Time reversal flips the direction of temporal progression, running the equations of motion backward, from future to past. In everyday physics, local phenomena often break individual symmetries. For instance, the weak nuclear force violates spatial parity and time reversal symmetry independently. However, mathematical quantum field theory dictates that the combined transformation of charge, parity, and time, CPT taken together as a unified operator, must strictly hold true across all fundamental physical interactions. If a theory breaks global CPT symmetry, it threatens to undermine Lorentz invariance, causality, and the basic consistency of relativistic quantum mechanics. This foundational symmetry gives rise to a profound cosmological question regarding the Big Bang. In standard modern cosmology, the universe is assumed to originate at a single temporal point, t equals 0, and expand outward into the future in a single direction. However, from a rigorous mathematical standpoint, a universe that begins at t equals 0 and only evolves forward in time breaks overall CPT symmetry across the full temporal axis. To preserve complete, unbroken CPT symmetry across the ultimate origin of space and time, the Big Bang should not mark a one-sided boundary where existence suddenly begins out of nothing. Instead, it should represent an inverted reflection point, or a cosmic mirror. This theoretical insight forms the foundation of the CPT-symmetric universe model. According to this hypothesis, the Big Bang gave birth not to a single isolated cosmos expanding in one direction, but to a twin pair of universes emerging simultaneously from the primordial singularity. On our side of the Big Bang, space expands forward into what we perceive as positive time, populated predominantly by ordinary matter, protons, neutrons, and electrons. On the other side of the Big Bang, a mirror universe expands in the opposite temporal direction, running into what we would mathematically define as negative time. In this anti-universe, the arrow of time flows in reverse relative to our local frame of reference. Furthermore, because of charge conjugation, this inverted partner cosmos is dominated by antimatter, antiprotons, antineutrons, and positrons, rather than conventional baryonic matter. Combined with parity inversion, every physical process occurring within the anti-universe operates as a precise, left-right flipped, antimatter-dominated, time-reversed counterpart to our own cosmos. If an observer could somehow inhabit the anti-universe and look back toward the Big Bang, their internal perception of time would feel entirely forward-moving and normal to them. From their perspective, their cosmos would appear to be expanding away from a hot, dense singularity into an expanding future. To them, our universe would be the strange, inverted mirror world, traveling backward into negative time and filled with anomalous matter. The two universes exist in perfect topological and physical equilibrium, maintaining total global symmetry across the origin point of space and time. Beyond its aesthetic mathematical symmetry, the CPT-symmetric universe model offers compelling theoretical solutions to several major outstanding mysteries in observational cosmology, most notably the nature of dark matter and the problem of cosmic inflation. In the standard cosmological model, dark matter constitutes roughly 85% of all matter in the universe, yet its fundamental identity remains completely unknown because it does not interact with light. Scientists have proposed exotic hypothetical particles, such as weakly interacting massive particles or axions, but decades of direct detection experiments have failed to find them. The CPT-symmetric model provides an elegant alternative mechanism that requires no exotic, unverified new particles. For quantum mechanics to remain mathematically consistent in a CPT-symmetric universe, the spectrum of fundamental particles must include a specific type of neutrino known as a right-handed or sterile neutrino. Standard particle physics observes only left-handed neutrinos, neutrinos whose quantum spin points opposite to their direction of motion. In the CPT-symmetric universe model, the Big Bang naturally produces massive right-handed neutrinos in exact mathematical balance with left-handed particles. Calculations performed by Boyle, Finn, and Turok demonstrate that one species of these heavy, stable right-handed neutrinos would be produced during the Big Bang with precisely the correct abundance, mass, and gravitational characteristics to account for all the dark matter observed in our cosmos today. Under this view, dark matter is not an exotic unknown substance, but a natural, inevitable consequence of preserving CPT symmetry across the Big Bang origin. Furthermore, this model challenges the necessity of cosmic inflation. As discussed in previous sections, standard cosmology relies on an epoch of exponential inflation to explain why our observable universe appears so flat and thermally uniform. However, in a CPT-symmetric framework, the presence of the mirror anti-universe naturally imposes mathematical boundary conditions at the singularity that smooth out spatial variations and enforce large-scale flatness without requiring a speculative inflaton field. It is essential, however, to contextualize this hypothesis with rigorous scientific hedging. The CPT-symmetric universe model is an extraordinarily elegant theoretical proposal, but it remains a subject of ongoing debate among theoretical physicists. Direct experimental verification presents formidable challenges because the mirror anti-universe exists on the other side of the temporal origin itself, completely inaccessible to direct observational instruments or light-based signals. Scientists are currently testing the model indirectly by refining measurements of neutrino masses and searching for specific cosmic signatures. If future particle detectors measure the absolute masses of neutrinos and find values that contradict the strict mathematical bounds predicted by CPT symmetry, this specific mirror universe model would be ruled out. The CPT symmetric universe hypothesis demonstrates how theoretical physics redefines what might exist on the other side of our cosmos. It suggests that the true boundary of our reality may not be a physical horizon located billions of light-years away in spatial distance, but a temporal mirror at the beginning of time itself, hiding an entire antimatter cosmos expanding into the past. As we survey these diverse hypotheses, ranging from infinite spatial continuation and compact topological loops to eternal inflation, higher dimensional branes and temporal mirror universes, we inevitably arrive at a profound methodological crossroad. Where does physics end, and where does philosophy begin? When scientists construct mathematical descriptions of regions beyond our particle horizon, are they engaging in legitimate empirical science? Or are they stepping into the realm of untestable theoretical speculation? To answer this question, we must carefully examine the foundational philosophy of science, specifically the criterion of falsifiability and the nature of scientific inference. In the 20th century, philosopher of science Karl Popper established one of the most influential frameworks for defining scientific knowledge, the principle of falsifiability. Popper argued that for a hypothesis or theory to be considered genuinely scientific, it must make specific, testable predictions that can, in principle, be proven false by empirical observation or experiment. If a theory is constructed in such a way that no conceivable observational result could ever contradict it, then, according to Popper's criterion, that theory resides outside the boundary of empirical science. When applied strictly to cosmology, falsifiability presents an immediate conceptual challenge regarding the unobserved universe. By definition, the boundary of our observable universe, the particle horizon located 46.5 billion light-years away, marks the absolute physical limit of signal transmission. No photon, neutrino, or gravitational wave traveling at or below the speed of light can convey information from beyond this barrier to our detectors on Earth. Because we cannot collect direct observational data from regions outside our horizon, any specific statement regarding what exists directly within those hidden spaces appears, at first glance, fundamentally unfalsifiable. Critics of multiverse theories and extreme cosmological extrapolations, such as physicists George Ellis and Paul Steinhardt, argue that proposing unobservable regions filled with infinite duplicates, bubble universes, or inaccessible extra dimensions risks eroding the empirical foundation of physics. They caution that if theoretical models rely on unobservable entities to explain local phenomena, such as using an infinite multiverse to explain why the physical constants of our universe appear fine-tuned for life, science risks losing its predictive authority. Under a strict Popperian view, if an idea cannot be directly tested or potentially refuted by observation, it should be categorized as theoretical metaphysics or philosophical speculation rather than hard physics. However, many modern theoretical physicists and cosmologists contend that the strict Popperian definition of falsifiability is overly simplistic when applied to fundamental physics. They argue that a theoretical entity does not need to be directly observable to be scientifically valid, provided it is an inevitable, logical consequence of a broader physical theory that is directly testable and falsifiable within our local observable domain. Consider, for example, the physics of black holes. We can never directly observe what happens past the event horizon of a black hole, because no light or signal can escape from within that gravitational boundary to inform an outside observer. Yet physicists confidently construct detailed mathematical models describing the interior spacetime of black holes. We accept these models as legitimate science because they are derived directly from Albert Einstein's general theory of relativity, a theory that has been repeatedly tested, verified, and confirmed with incredible precision through observable phenomena outside event horizons, such as gravitational lensing and gravitational wave detection. The same logical principle applies to what lies beyond our cosmic horizon. Cosmologists do not arbitrarily invent models like cosmic inflation, dark flow, or topological curvature merely to speculate about the unobserved world. Instead, these theoretical models are developed to solve concrete observational puzzles within our visible universe, such as the extraordinary uniformity of the cosmic microwave background temperature, or the precise density distribution of galaxies. If a cosmological framework, such as cosmic inflation, makes specific predictions about local observable phenomena that are subsequently confirmed by high-precision measurements from space telescopes, then the unobserved consequences of that same theory gain strong indirect scientific credibility. If the mathematical equations that accurately predict the specific pattern of temperature fluctuations in our sky also dictate that inflation must be eternal, generating infinite bubble universes beyond our sight, then the existence of those distant bubbles becomes a legitimate scientific inference rather than a baseless guess. This highlights the true power and purpose of theoretical inference in physics. Human understanding has never been strictly limited to what our eyes can immediately touch or see. Historically, many of the greatest breakthroughs in physics began as pure theoretical deductions far beyond the observational capabilities of their time. When Democritus proposed the existence of atoms, when James Clerk Maxwell predicted invisible electromagnetic waves, or when Peter Higgs hypothesized the existence of the Higgs field, these concepts existed purely as mathematical inferences long before experimental technology evolved to detect them directly. Furthermore, continuing to theorize about what lies beyond our horizon drives the advancement of mathematics and fundamental physics. Attempting to model the unobserved forces scientists to reconcile quantum mechanics with general relativity, pushing the boundaries of string theory, quantum gravity, and field theory. These theoretical efforts force us to refine our analytical tools, develop more sophisticated space instruments, and design new statistical methods for analyzing subtle cosmic anomalies. Therefore, when evaluating hypotheses about what exists on the other side of the universe, we must maintain a carefully balanced scientific perspective. We should avoid dismissing theoretical models simply because they extend beyond our current observational horizon, while simultaneously refusing to treat unproven mathematical extrapolations as established facts. The space beyond our sight represents the ultimate testing ground for human intellect. It reminds us that science is not merely a static collection of direct observations, but a dynamic, evolving process of building logical frameworks that allow us to deduce the hidden architecture of reality. Whether the unobserved cosmos turns out to be an endless sea of galaxies, a topological loop, a collection of inflating bubbles, or a higher dimensional bulk, our ongoing effort to model it demonstrates the remarkable capacity of human intelligence to reach out into the unknown using the enduring language of physics and mathematics. Our exploration of what lies beyond the observable universe reveals the vast scale of modern theoretical physics and cosmology. We began our journey at the absolute boundary of human sight, the 46.5 billion light-year particle horizon, and the ancient wall of the cosmic microwave background radiation. From this observational boundary, we examined the most grounded scientific deduction, the hypothesis of infinite spatial continuation, where the cosmological principle suggests that space simply stretches onward with more galaxies, stars, and cosmic web structures. We then ventured into more exotic geometric and theoretical possibilities. We explored cosmic topology, where a closed three-torus geometry could mean that the universe loops back on itself, making the distant side of space a repeating image of our own local neighborhood. Through the lens of eternal inflation, we looked at the multiverse paradigm, where our entire visible cosmos is merely a single bubble floating within an expanding sea of pocket universes, each potentially operating under distinct physical laws. We evaluated potential observational signatures, such as the controversial dark flow phenomenon, where massive structures beyond our sight might exert long-range gravitational forces on our local galaxy clusters. We expanded our geometric perspective through string theory and Brane cosmology, considering whether the true edge of our universe is not a spatial distance, but the boundary of a three-dimensional membrane floating inside an 11-dimensional bulk. Finally, we turned back to the beginning of time itself, examining the CPT-symmetric universe model, where a mirror anti-universe dominated by antimatter expands backward through time from the Big Bang. Ultimately, these diverse models illustrate the boundary where empirical observation meets theoretical inference. While light speed constraints may permanently prevent human instruments from receiving direct signals from beyond our horizon, mathematical physics empowers us to construct logical models of the unseen cosmos. As telescope technologies advance and particle physics deepens our grasp of fundamental reality, we continue to push the boundaries of knowledge, seeking to understand our true place within this vast, magnificent, and largely mysterious cosmos.